All right, so welcome to lecture 7 of 124 Physics 1A. So the topic, as you can see, there's friction in circular motion. So seemingly it looks like a new topic, but it's actually still just a continuation of what we've been learning last week about forces and free body diagrams and how to use free body diagrams in solving problems involving forces. Except that this time we will be focusing on a specific kind of motion called circular motion. So last time we already learned about free body diagrams and how to use this to solve motion along a straight line, right? Which we call linear motion. It could be either just along the horizontal or vertical axis, or it could be along an inclined plane. So last time we already looked at how we can solve problems such as this, an object being pulled, so there's tension force, or an object that's sliding down an inclined plane. We didn't have quite enough time to go over applying free body diagrams to systems with more than one object. So let's start our lecture with that. We intuitively, if two objects are connected together and they move together, then it just makes sense that their acceleration should be the same, right? Because they're moving at the same time. So objects should have equal acceleration and velocities, magnitudes at least. And if the objects are connected by a string or a cable, then the tension throughout that rope or string or cable should be the same, because it's the same, it's the same string that connects these two objects. And as these two objects move, the tension will be the same all throughout. Okay. We've seen one example of this. If you remember those two objects that are connected, and we looked at this example last time, where we had two masses and they were connected by a string and they were being pulled to the right. And we've seen that the technique for solving a system with more than one object is to draw a free body diagram for each of the objects. Okay. So if you have two free body diagrams, then you should also apply Newton's second law to each of the free body diagrams. Newton's second law, again, is this net force is equal to mass times acceleration. Yeah. Okay. Again, since you have two free body diagrams, you need to use a coordinate system for each of the free body diagrams. You have to be consistent with, if you choose the x-axis to be along the horizontal and the y-axis to be along the vertical for one object, the second object should also have the same orientation for the x and y axes, even though you can assign different directions for negative and positive directions. Yeah. Okay. Why can the directions be different? Well, we will assign the positive axis to be in the direction of acceleration. Yeah. Okay, so let's look at an example, and this is similar to the question in the workshop. You have these two objects, 2 kilogram and 3 kilogram masses. They're connected by a string and they're attached through a pulley, which is frictionless. Okay. Yeah, obviously, if you let go of this system, the 3 kilogram mass is heavier. So the 3 kilogram mass will move downwards, and because it's connected to the 2 kilogram mass, then this 2 kilogram mass will move to the right. Yeah. Okay. We want to find the acceleration of the two masses and the tension in the string. Okay. So two objects will require two free body diagrams. Okay. So draw a free body diagram for each of the objects. So this just summarizes what I showed in the previous slide. Just be conscious the acceleration. Notice how the direction of the acceleration is different for each of these masses. Okay. So how do we set up our coordinate system for each of these accelerations? Let's look at that in the solution. Okay, first let's draw the free body diagram of this 2 kilogram mass. Yeah. should look like this. Any object that has mass should have a weight force. Weight is always directed downwards. The 2 kilogram mass is supported by the surface. Okay, you have this surface that's physically supporting the 2 kilogram mass, and hence it should have a normal force. And of course, tension on the string. Okay? The tension is always directed away from the object, and therefore the tension is directed to the right. Your object is the 2 kilogram mass in this case. For the 3 kilogram mass, what are the forces on the 3 kilogram mass? Weight force and tension, yeah? It doesn't have any normal force because there's no physical surface that's supporting this 3 kilogram mass. So you only have these two forces. Again, tension is always directed away from the object. And if your object is the 3 kilogram mass, the tension should be upwards, yeah, along the string, of course. And weight force is, of course, downwards. Okay, now we set up our coordinate axes. X-axis should be in the direction positive x-axis. Notice how the positive x-axis is in the direction of the acceleration. This is for the 2 kilogram mass. Okay, if we set up the x-axis for the 3 kilogram mass, notice how your x-axis is still in the horizontal position. Your y-axis is still in the vertical position. But because your acceleration is directed downwards, the positive y-axis should follow the direction of acceleration. Yeah. Yeah. It's a very important concept, because if we don't follow the direction of acceleration, then when we set up Newton's second law of motion, we also have to consider then where is positive and negative acceleration. But by following the direction of the acceleration, we can set up the Newton's second law of motion without thinking about the direction of acceleration and just looking at the direction of our forces in the free body diagram. Yeah, so now let's set up Newton's second law of motion. For the 2 kilogram mass, this is Newton's second law, net force is equal to mass times acceleration. Looking at your free body diagram here, it's only tension that will contribute to the acceleration of the 2 kilogram mass, yeah? The normal force and the weight force will actually cancel each other out because you don't have acceleration along the vertical, yeah? So the equation for the 2 kilogram mass is just tension on the left-hand side equal to the net force, and the right-hand side, you have the mass times acceleration. Okay, for the 3 kilogram mass, Newton's second law of motion, again, net force is equal to mass times acceleration. But notice here in your free body diagram, you only have two forces, but notice how the tension is negative, yeah? The tension is negative. Why is the tension negative? The tension is opposite the direction of the acceleration, and therefore opposite the assigned positive y-axis. Right? And notice that in these two equations, the acceleration was always positive because we've assigned the direction of the acceleration to be the positive direction. So we didn't have to worry about whether this acceleration is negative or positive. We only had to worry about whether the force is in the direction of the acceleration or opposite the direction of acceleration. Yeah. Cool. Now we have these two equations. And we don't know two things, right? We don't know the tension on the string. It's not given in the problem. And we don't know the acceleration. That's in fact what we need to find, right? You have two equations and two unknowns. You can then use these two equations simultaneously to eliminate one of the things you don't know, right? So I just write here again these two equations. And then if I add them both up, then tension cancels out. Or you can use, yeah, you can, there are several ways of dealing with simultaneous equations. Yeah, this is just one method where if I add them both together, the tension will cancel out, and I just have this equation containing acceleration and the masses. Yeah, rearranging therefore gives me the acceleration, 5.9 meters per second squared. Cool. All right, any question about this? Of course, once we've determined what the acceleration is, we can then use either of these two equations to find the tension. So for the second question, find the tension on the string, right? You can use, first equation is more intuitive because it's a simpler equation, and you can directly find the tension on the string. All right. Any question at all, or we can move on. Yeah, so try this. I'll give you a couple of minutes to sort of try and figure out this example of the elevator. So you have here the mass of the elevator cart is given, and the mass of a counterweight. So the elevator car is attached to a counterweight by a rope that goes over a pulley. Okay. So if you notice, the mass of the car is bigger than the mass of the counterweight. So naturally, the car will fall down. And since they are connected by the same rope, the falling elevator cart will pull the counterweight upwards. And so you have these directions of acceleration indicated in the diagram. So calculate the acceleration of the car and the counterweight, elevator car and counterweight.
All right, we'll go back to the previous slide.
Yeah. And you might need, the masses are written here. So just if you get an acceleration of 0.684 meters per second squared, then that means you've done the right thing. Okay, should we look at the solution for this? Okay, so again, the two objects, the elevator car, you can say that this is object one, and the counterweight, you can say that that's the second object. They're connected by the same rope, and therefore the tension on this rope will be the same, and the acceleration of the car and the counterweight should be the same. Okay, so we draw the two free body diagrams, one for each object. Okay, there's no physical surface supporting any of these objects, so you only have weight force that is always directed downwards, and tension force. Tension force is always directed away from the object. Right, so we assign then the positive x and positive axes. Direction of acceleration will be positive. Yeah, we know the elevator car will move downwards and the counterweight will move upwards. So we assign the positive y for the elevator to be downwards. Okay, and then for the counterweight, we assign the positive y direction to be upwards, yeah, in the same direction as the accelerations of each of the objects. Right, so just rewriting here, our free body diagrams with our axes. Okay, we know we then apply Newton's second law of motion. Net force is equal to mass times acceleration. Okay. For the elevator weight, we have a positive weight force, okay, because we assigned downwards to be positive, and so you have a positive weight force but a negative tension. Yeah. And for the counterweight, right, we assigned a positive direction to be upwards in the direction of the acceleration, and therefore we have a positive tension and a negative weight force, right? Yeah. Right. To figure out what the weight is, that we use the mass of the car and the counterweight. So we just rewrite then our Newton's second law of motion. Instead of weight force, we have mass of the elevator car times gravitational acceleration, and the same thing for the counterweight. Mass of the counterweight times gravitational acceleration. We now then again have these two equations, which allows us to solve the two things we don't know, the tension and the acceleration. Yeah. Right, so if I rewrite, just rewriting these two equations one after the other, I can see that there's minus tension in one and plus tension in the other. So I can subtract, I can add these two equations, causing the tension to cancel each other out. And I have this equation which contains only acceleration and masses, okay, which you can then rearrange to solve for the acceleration. Right. Okay, once you know the acceleration, you can use either of these two equations. You should get the tension. Yeah, the small difference in the tension you get is just comes down to rounding of the acceleration and how how they're arranged in this equation here. Yeah, this is just rounding to 3 significant figures. Cool. Any question about this example or two objects in general, like applying Newton's second law of motion to two objects? Okay, seems like, yeah, seems we're happy to move on in this case. All right, no questions. Okay, so let's now move on to, applying Newton's second law of motion to circular motion. So how will we modify net force equals mass times acceleration an object moving in circular motion. For this topic, we will consider only a special kind of circular motion called uniform circular motion. A circular motion, of course, it just makes sense. The object traces a circular path. It's uniform because the circular path that the object traces has a constant radius. And as the object rotates and traces this circular path, the object has a constant speed. So this uniform refers to constant radius and a constant speed. Okay. Right. So here the green arrow here shows you the velocity, the instantaneous velocity of the object as it rotates. Okay. Notice how the length of the arrow, the green arrow is the same, meaning the speed is the same, but the direction of the velocity changes at each point along the path. And therefore the instantaneous velocity will be different in terms only of the direction, but the speed will be the same. Okay, and the direction of the velocity is always tangent to each point in the circular path. Right. So if we draw the whole path, it looks like this. You have the velocity, instantaneous velocity changing throughout the circular path. Okay, the length of the arrow should be the same, meaning that the speed would be the same. Oh, yeah. Cool. Yeah, good. And then, okay, even if the speed is the same, you will still have some acceleration, yeah, because the direction is changing, meaning the velocity is still changing even if the speed is constant, right? Velocity being speed plus direction. Since the direction is changing at each point, then there should be some acceleration at each point in the path. And this acceleration is what we call the radial or centripetal acceleration. And it's called as such because the acceleration is always directed towards the center of the circular path. Yeah. All right, this acceleration should be related to the speed. Okay, the radial acceleration is equal to v squared over r, where r is the radius of the circular path, and v is the speed of the rotation. Okay. Right. How do we define this speed v? We call this the tangential or linear speed. Right. Well, we also still know that speed is equal to distance over time. Right. So that's the basic definition of speed, distance over time. But if we apply that definition to our circular motion, the object will cover a distance equal to the circumference of the circular path. Yeah. And so the distance is equal to 2 pi r, which is the circumference of a circle, where r is the radius of the circle. Okay. And then the time will be defined by what we call the period, which is the time for one revolution around the circle. Okay, and so the speed is then equal to 2 pi r over the period t. Right. We can also then define a quantity called frequency, which is the number of revolutions per time. Okay, which is just the inverse of the period. If period is the time for one revolution, then frequency is the inverse of this period. It's the number of revolutions per time. Right, so defining all these quantities, right? We know that there is centripetal acceleration, or acceleration that's always directed towards the middle of the circle. And what does Newton's second law of motion say? If you have acceleration, what should you have? Net force, right? You will only have acceleration if you have a net force. Okay? And since you have acceleration directed to the middle, to the center of the circular path, then you should also have acceleration, a net force, and the direction of this net force will be in the same direction as the acceleration. Yeah. So it should be in the same. So if you have radial acceleration towards the center, you should also have a net force that's in the same direction as the acceleration. And that's given by Newton's second law of motion. So if you look at Newton's second law of motion, you will only have acceleration if you have net force. And mass is just a scalar quantity. So the direction of the acceleration will always be in the same direction as the net force, right? So therefore, net force should also be towards the center of the circle in the same direction as the radial acceleration. So in terms of circular motion, Newton's second law of motion can be modified by using the expression for the radial acceleration, because we can easily measure the radius of the circular path, and the tangential speed can also be easily measured, right? We just count how many revolutions there are and count the time it takes for one revolution. So we can easily figure out what this tangential or linear speed is. The mass is also, of course, easily measured. Okay. Right, of course, we will still use the direction of acceleration to be the positive direction as we've been using. Right, so let's look at an example to apply the whole concept of Newton's second law of motion being applied to circular motion. So we have here, so you have here a string and you have an object. We know, like, if we rotate this overhead, just like in the figure there will be, you know, the object, the pail will move in a circular path. The question is, how much should you pull? You know, it will only rotate above you if you pull on the string and provide some initial velocity. Yeah, but if you don't pull quite enough, if you don't apply enough tension, there's sort of like it will not rotate in this uniform circular motion fashion. And so this is what we want to estimate in this problem. Estimate the force, you know, how much you should pull on the string in order for an object, 0.150 kilogram object, ball, to revolve in a horizontal circle of radius 0.6 meters. Okay, and the ball makes 2 revolutions per second. We can ignore the string's mass, meaning we don't have to consider the weight of the string. So we don't have to put the force, weight force of the string. Okay, so it's the same problem written there. Let's just write down the given information, yeah? What's given? We're given the mass, 0.150 kilograms. We're given the radius of the circular path, which is usually defined by how long the string is, 0.6 meters. Okay, and then the other thing we're given is this 2 revolutions per second. Okay, 2 revolutions per second, that's the frequency. And we want to find the tension on the string. We of course know Newton's second law of motion in radial form. Right, so we pretty much know the mass and the radius of this circular path. These 2 quantities are given. And hey, we need to find the speed, the linear or tangential speed, in order to figure out what is this net force in the radial direction. Okay. What we are given only is the frequency 2 revolutions per second. So how do we deal with this? Okay, if we look at the diagram, the tension on the string is, of course, the radial force that causes the object to go in the circular fashion. And so this radial acceleration is then provided by this tension force. Yeah, so tension provides centripetal force or radial force. So your tension force will be equal to mv squared over r. Yeah, Newton's second law of motion, the net force along the radial direction will be equal to mv squared over r. Okay. And so the tension force is what's providing this radial, is the radial force. So tension is equal to mv squared over r. Okay, the only thing that's stopping us from calculating tension is this linear speed. So we need to figure out what is this v, linear or tangential speed. Okay, I'll use this pace. We know speed is equal to distance over time. Okay. The distance is, of course, the circumference of the circle. 2 pi r over the time will be the period. Yeah. Right, so we can sort of figure this out because the circumference, we can calculate that given the radius. And the period is equal to inverse of the frequency. The frequency is 2 revolutions per second, so period will be 1/2 or 0.5. Right, so your linear or tangential speed will be 2 pi this will be 7.54. Right? Okay, does that make sense? How to get the linear speed from the frequency? What we can see here is the revolutions per second is actually also a measure of, it's a form of unit for speed. Yeah, so we can see here that revolutions per second is also a unit for speed, okay, being because it's distance over time. Yeah, 2 revolutions gives you the distance and seconds give you the time. Right, so how do we convert? So yeah, this one I've worked out, this is the long way of working out what the linear speed is, but realizing that revolutions per second is also just a unit for speed. So next time you encounter revolutions per second, it will just be a unit conversion type of thing, yeah? But we need to then convert, the question is how to convert revolutions per second to meters per second. Okay, we need some conversion factor. I'll just use this extra space. So converting revolutions per second to meters per second. Okay, you can use the conversion factor. One revolution is equal to 2 pi r. Meters, yeah? So for example, 2 revolutions per second, okay? You can just write that down as 2 times 1 revolution per second, 2 times 2 pi r meters over second 4 pi r. Okay, and for our specific problem, for r is equal to 0.6 meters, then 2 revolutions per second is equal to 4 pi times 0.6. We'll also give you the 7.54 meters per second. Right, so you can, this conversion factor will be quite useful when you're converting revolutions per second, or later on revolutions per minute, into meters per second. Okay. All right, so now we've figured out what our v, linear or tangential speed, is. So we then substitute everything to our equation for the tension force. So mass 0.150 times 7.54 squared divided by 0.6 gives you a tension of 14.2 newtons. Right, any question about this example? I guess the key thing, there are two key things here. The radial equation for Newton's second law of motion is this one. So the first thing you need to figure out is, what is this radial force that provides the radial acceleration? And then try to figure out what's this radial, or this tangential or linear speed v. Okay. And if you're given revolutions per second, we learned that you can actually just convert that to meters per second by using 2 pi r as the conversion factor. Yeah, so for different scenarios, there can be, it's quite intuitive to sort of figure out what is this force that creates this radial acceleration. We've already seen the first example of the object on a string. Okay, in that case, the tension provides the radial acceleration, and so Newton's second law of motion becomes tension equals mass times radial acceleration. Right, the tension is of course directed towards the center of the motion in the same direction as the acceleration. We'll also encounter some scenario where an object on a rough surface meaning there's friction present. Okay, if the object moves in a circular path through a rough surface, we need to figure out what is the centripetal force or radial force that will cause this object to have this radial acceleration. A good example of this is a car that is turning on a flat bend with a rough surface. So you have there, the car should have this radial acceleration that will make it turn around the bend instead of the car, instead of the car losing the turn or not making the turn and slipping through the bend. So if we look at the free body diagram of this turning car, of course it will have weight force and the road is supporting it. So there's a normal force provided by the road, but the frictional force provided by the surface, the rough surface, will be this tangential force that will cause the car to turn around the bend. So for objects on a rough surface that's making this circular path, okay, the centripetal force is friction, and of course the right-hand side will still be mass times radial acceleration. Right. Cool. Right. In vertical motion, like if the motion involves a Ferris wheel, or if, for example, I whirl this in a vertical circle like this, okay, in a vertical motion, there will always be weight force coming into the net radial force. Yeah, weight force will always contribute. So this figure is a very good example. So there will always be weight force along the radial direction. So if you notice here, it's easy to see at the top of the Ferris wheel, the weight force always downward. So the weight force is directed to the center of the circular path. But you also have this normal force. If you have a seat or a car that's supporting the object, then you have this normal force that's perpendicular to the surface. If the object is supported, you should consider the normal force. So for this particular case, on top here, the net radial force will be the weight force minus the normal force. Okay. At the bottom of the circle, you'll also have this normal force that's always perpendicular to the surface, and the weight force that's always downwards. Okay. So the net force here will have to be the normal force minus the weight force. So here, weight, and here, so notice again how the positive forces are in the direction of the radial acceleration. So positive weight on the top, okay, and then positive normal force at the bottom. Okay. Positive directions are in the direction of the acceleration. Right. Okay, so I guess I'm showing these examples because in any circular motion where you need to use Newton's second law of motion, really the problem is what is the radial force that you will use in order to calculate for whatever's being asked, like for the tangential speed, for example, or if you're being asked to find what is this radial force. Yeah, so that's why in these scenarios here, I'm enumerating what are the radial forces in each of the scenarios that you might encounter. Okay, there's one special scenario called a banked, if the object rounds a curved, yeah, in a normal level surface, we only have these two forces on the car, right? Let's say there's no friction. You only have the weight force that's downwards and a normal force that's upwards. Okay? But if we, for example, we bank the curve so that you have some angle, this angle theta relative to the horizontal, the free body diagram will change such that the normal force will now have like this orientation, because the normal force is always perpendicular to the surface. And since your surface is inclined, your normal force will then be oriented differently as when you have a level surface like this. Okay, what happens then is, how do we deal with this bank curve? So notice if your car is rounding a bend and the bend is banked, the acceleration will still be, if your car is rounding this bend, okay, and you have this car here, your radial acceleration would still be towards the center of this imaginary circle formed by this bend in the road. Okay, but then your normal force will have some angle relative to the centripetal or radial acceleration. So if we assign the acceleration to be in the x-axis, notice how your normal force will then have an x component and a y component. So if your acceleration is in the direction of positive x-axis and this is your normal force, notice how your normal force should have an x component and a y component. So just drawing the normal force in a neat free body diagram. Okay, your x component for the normal force will be given by this n sine theta, and your y component is n cosine theta. It's very similar to the inclined plane scenario that we learned last lecture. Yeah. So then if we solve for Newton's second law of motion in the radial form, okay, right, along the x-axis, which we assign to be in the direction of the acceleration, and the acceleration is the radial acceleration. It's therefore normal force, the x component of the normal force, that is equal to the mass times the radial acceleration. Okay. And for the y component, because we've assigned the y component to be in this direction, and you don't have motion along this direction, yeah, you want your car to just round the bend, having this centripetal acceleration along the x-axis, then the acceleration along the y-axis should be 0, and so the y component of normal force should balance out the weight force of the car. And the similar scenario will apply for a airplane that's tilted and it's making a turn. It will be the same as a car rounding a bank curve, but in this case, there's no normal force. The normal force is replaced by this lift force because of the airplane's, engine. And so you have, instead of a normal force, you have this lift force, but the concept is still the same. You have the y component of lift force and the x component of lift force. And so you have your, along the x components, you have the lift force equal to the radial acceleration. And along the y, you don't have motion along the y because you want your airplane to bank and make the turn towards the center of the radial circle, radial acceleration. And so you have the weight force equal to the y component of the lift force. Okay. So we'll look at examples of this in the workshop. I think there's a problem or two about applying the radial component of Newton's second law of motion, but it's really all about just figuring out what is the force that will provide you this radial acceleration, and the solving of the problem is the same as the techniques that we've been learning previously. But we don't have time yet. There's an example here, which is just a coin that's going in this flat, rotating in this flat surface. Okay, we don't have time to look at the solutions of this in detail, so we'll look at the solution of this in the next lecture as a review problem. Okay, so I'll see you tomorrow for lecture 8, and have a good day, everyone.